So today we're going to look at some applications of calculus and how we can apply those to mainly the field of economics. So we're going to continue talking about some concepts that you would have gone over in Business Math 1. So we're going to review a few of those here before we begin. So in Business Math 1 or the class you take before this one, you probably should have talked about some various economic formulas. Okay, the first one is the cost function, otherwise known as the total cost function. We usually use C of X to represent that total cost, but it is simply the total cost in producing X units. So an example of a cost functions can be linear or not, but let's look at a linear cost function. So if we had a cost function that looked like this, okay, that's a linear cost function where the fixed cost is $500 and the variable cost for each unit is $20, okay? And so if I was asked to find C of 50, this would be the total cost of the first 50 units. So it's not the cost per unit, it would be the total cost for the 50 units, okay? So cost is representative of what a business has to pay in order to make the items. Revenue, on the other hand, this is often confused with profit. It is not the same, okay? Revenue is the money brought in from the sale of X units. It doesn't necessarily mean that you get to keep that money if you're the business owner or pocket it, because you still have to pay expenses or costs. But it is the money brought in from the sale of X units. And just like cost, it can be a linear equation or sometimes not. Okay. But the bottom line is we always want to really talk about profit. And so not surprisingly, we use P of X to describe profit. But P of X is always, or profit is always, you take the revenue you brought in from the sale of X units and you subtract off the costs that you needed to produce those items, okay? And so this is actually the money a company gets to keep. From selling X units. So we want to make sure that we understand the difference between revenue and profit. A lot of times, even in like advertisements or stuff like that, I'll hear things like, we're a multi-million-dollar company, when actually they mean that they are a multi-million-dollar in sales company. You can be a multi-million-dollar company and still have costs that exceed those multi-millions. So we want to make sure we're talking about profit when we think we are. So those are all review, those are all algebra topics. So what we're going to discuss that involves calculus is some other versions of cost. The first being the marginal cost. So the marginal cost is the cost in producing an additional unit given that a certain amount of units has already been produced. So in other words, let's say we have already made 1,000 items of whatever it is that we're making, then the marginal cost would be what would be the cost of that next one, the cost of one more unit, in other words. So in my 1,000 example, if I've already made 1,000 units, it would be what would the cost of that 1,001st unit be? So what we're really talking about, by the way, the cost of the next unit might not be the same for different production levels. Okay, sometimes different levels of production, the units cost a different amount, okay, for various reasons. Sometimes you have to hire more people. Sometimes you need a new machine. Sometimes you have streamlined your processes and your costs are going down. I mean, there's all sorts of things that can affect how much the cost of a particular item could be. But marginal cost is always, since it's the cost of the next item, it's a rate of change. And so it's simply just the derivative of the cost function. So when you see the word marginal, you need to realize that's synonymous with derivative. But the derivative, remember, represents a rate of change or the slope of the tangent. So if we want the rate of change of costs at a particular production level, then we use this marginal notation. Okay, and we're going to use our prime notation to indicate that we have that we're discussing marginal cost. Okay, so let's take a look at an example so I can show you kind of what we're going to be finding the derivative of. So let's say that a company makes CDs at a cost of $2,000 plus 2x minus 0.0001 x squared, where x is the number of CDs, and what I want you to do is I want you to compare the exact cost of the 1,001st CD to the marginal cost at that level. Okay, so for exact cost, I don't actually need calculus. Okay, for exact cost, I can actually just use algebra. So I'm going to start with this. I'm going to start with C of 1001 since that's the item that I want, but keep in mind this won't be my answer because this would actually be the cost of all the first 1,001 CDs. It's a total cost function. And remember, all I really want is the specific item 1,001. Okay, I don't want items 1 through 1,001. So to get to the one that I want, I'm just going to take off C of 1,000, because notice that would take off items 1 through 1,000, leaving only the 1,001st, which is what I wanted. Okay, so let's see if we can figure out what that is. So we're going to use our calculator. I'm going to project it here in just a bit. So let's see if we can figure out C of 1,001. Okay, by the way, that means we're going to replace X with 1,001. Okay, so let's figure out what that is on our calculator. So make sure that we can kind of see this and it's not too blurry. It's kind of hard to get this calculator and not have it be glary. Okay, so we want 2,000 plus 2 times 1,001 minus 0.0001 times 1,001 squared. And notice we want to round this since it's money, right? So notice we're going to get $3,901.80 if we round it. Okay, let me slide the paper over. Okay, we also need to figure out C of 1,000. And notice we just want the same equation with 1,000 plugged in this time. Okay, so a trick on your calculator is if you want the calculator to do something similar to what you've already had it do, you can actually push the second button that's under the y equals and enter, and notice how it has this black arrow, and then I'm moving the cursor with my left arrow. All I really need to do is change all the 1,001s in the equation to 1,000. And this way is quicker, but if you just want to enter it all in again, you're free to do that also. So notice we get just an even 3,900. Okay, so the exact cost would be the difference between the two. So the exact cost of the item in question would be 3101.80 minus 3,900 for a difference of $1.80. Okay, this is the actual cost of that item. Okay, so let's compare that to the marginal cost at that level. So marginal cost means derivative. So first what we need to do is find the derivative of that cost function. Okay, so if you go back up to the top, so I'm going to kind of slide this down a little bit so we can still see it. Here's my original cost function, right? So the derivative of 2,000, remember 2,000 is just a constant, so the derivative of 2,000 is 0. The derivative of 2x is 2. And then if you try to find the derivative of that x squared term and you move the 2 to the front, you're going to get minus 0.0002 and then x to the first. Okay, so written a maybe little simpler way, it's negative 0.0002x plus 2. Okay, so now let's figure out what number we need to plug in. So marginal cost is the cost of the next item. Okay, so the number you plug into the derivative formula is actually representative of how many items have been made to this point. So in other words, 1,000 items have been made, and so if I find C prime of 1, it's actually literally going to be what I want. This would be actually the cost of the next unit, which is exactly the one that we want, right? It's literally the one after 1,000, which would be 1,001. So we would do negative 0.0002 times 1,000 plus 2. Okay, so let's go ahead and do that on our calculator. So negative 0.0002 times 1,000 plus 2. Okay, notice we get the same answer that we did above, and we're going to talk about that. But this is the cost we found from doing rate of change instead. Okay, so in this problem, they ended up being the same. Notice actual cost and the marginal cost at that level was the same. But just know it's not always completely perfect that way, but it should be close because actually the marginal cost is an approximation. That's what the squiggly equals means of the exact cost. Okay. Notice our calculation was a lot easier here as long as we knew how to find derivative, right? We only had to plug in one number. It was a lot quicker to do the marginal cost this way than it was necessarily to have to plug two numbers in the original and subtract them. Okay. So when you see the word marginal, you need to understand that that's a rate of change. Okay, so you want to know that that's the derivative. All right, so another type of cost that we've actually talked about this semester already, but it was just like a word problem at the end of one of the note sets, and that's average cost. Okay, average and total cost are not the same thing. Total cost is the total cost for making a whole bunch of units. Average cost is the average cost per unit for producing X units. Okay. It's a principle of big business that the more items you make, the less they're supposed to cost as you go on, but that's not always necessarily true, but that does happen a lot of times. That's how big businesses like Walmart are able to keep their costs low and so then pass that on to you, the customer, and sell things for cheaper than other people can. So let's say that it cost 100 grand to produce 1,000 units. I want you to think about how you would find the average cost per unit. If you know the total cost and you know how many units you made, it should be easy to find the cost per unit, right? You just take the 100,000 and you divide it by 1,000, okay? And you get an answer of $100, but it's $100 per unit. So like that example we just looked at, the average cost formula, if I want to know the average cost per unit, can always be found by dividing total cost by X. Before we do that though, I want to write notation-wise how you will see average cost. Notice there's C with a bar over it, and you literally read this as C bar of X. But C bar of X is average cost. Okay, in other words, we have to have a different notation so we don't confuse average cost with total cost. Okay, so the bar over the notation is how we distinguish between the two. Okay, so let's look at maybe a couple of, maybe a word problem about average cost. So let's say that you were making large manuals for some manufacturer, and the cost of printing X manuals is C of X equals 20,000 plus 10X. So first I want you to find the average cost equation. And I want you to find the average cost per unit if 1,000 units are made. All right. So let's start that. So the first thing is we need to find average cost, and that is C bar of X. And we find that by doing C of X over X. So we're going to take that cost equation of 20,000 plus 10X, and we're going to divide that by X. Okay. So this is an acceptable answer for the total cost. Okay. I just want you to know though, you can rewrite it, and later on we're probably going to want to. When you have a singular denominator, you're allowed to pull the pieces apart and write them over that denominator. In other words, this is equivalent to saying 20,000 over X plus 10X over X, but that would reduce to 10. Okay, so I'm going to circle both of these because actually this gives us an interesting look, right? It's basically the fixed cost divided by however many units you have, and then plus the extra $10 per item. Okay, but you get the same result there. That's actually why I circled them both. So for average cost, I would take either form, and so will my math lab. So now let's find the average cost for 1,000 units. I'm going to use this equation because I think it's easier. But if I divide that 20,000 fixed cost by 1,000 units and then I add $10 to it, I'm going to get 20 here plus 10, or $30 per manual. Okay. What if I asked you for the marginal cost instead? So find the marginal cost for a production level of 1,000. Okay, so notice marginal means something different than average, right? Marginal means, hey, I need to find the derivative of the original, okay? So recall, it's not on screen anymore, recall that C of X was 20,000 plus 10X. So if I want the derivative of a constant, whether it's large like 20,000 or not, is just 0, okay? And then the derivative of this is just 10. Okay, so in other words, this is the cost per manual. Okay, notice it's a steady cost. We won't always get just a constant for our slope, but this time we did because, frankly, the cost function was linear. When the cost function is other than linear, then you might get an equation here where the cost could, or the marginal cost rather, could be changing. But this is the cost per manual if previous manuals have already been produced. And so we also can come up with the marginal average cost. And just like the name implies, the marginal average cost will be the derivative of the average cost function. So notation-wise, it looks like this. C bar prime of x. So let's say that I asked you to find that C bar prime of x of the above example. In other words, I want you to take the average cost that you got, and I want you to take the derivative of it. Okay. So first, let's rewrite what we had, right? We had that the average cost formula was 20,000 over x plus 10. Okay. But remember from our derivative sections, we're going to want to rewrite this. We want to rewrite this guy right here so that we can do power rule on it, right? Anytime you have a fraction with x in the denominator, you need to think about rewriting it before you try to take the derivative. So I'm going to rewrite this as 20,000 x to the negative 1 power and then plus 10. So now I'm ready to find what I want, right, which is the derivative of this. Okay, so if I move the negative 1 to the front, I'm going to get negative 20,000. And then x to the negative 2 power. The derivative of 10 by itself is just 0. So I end up getting a rate of change that is negative, and that actually shouldn't surprise us at all, because what that means is that the average cost per unit is decreasing as more units are made. And that actually should make sense to us logically, right? Okay. So the average cost per unit is decreasing because basically they're probably streamlining their processes and getting quicker at it. Okay, so we also have concepts of marginal revenue and marginal profit. It's not too much of a stretch, but marginal revenue is going to be the derivative of the revenue. Okay, but it is also described as the revenue brought in by the sale of the next item. Okay, the word marginal, when it goes in front of a word, always means derivative. Okay, so just kind of remember that. So marginal profit, not surprisingly, is going to be P prime of x. And it will be the profit earned by the sale of the next unit. Interestingly enough, if you want P prime of x, you can take R prime of x minus C prime of x. In other words, that relationship where profit is the difference between revenue and cost actually works for its derivatives as well. Okay, so let's look at a couple more examples and make sure we know how to do maybe the little more challenging derivatives that you might find in this section. I would say really the only real difference between the derivatives you've been taking before and the derivatives in this section is, because it's real life data or close to it, there's decimals involved. They're not as cookie cutter nice equations as they were before. But let's say a company makes drill bits and the daily cost function is C of x equals 1,000 plus 25x minus 0.01 x squared, where x is the number of drill bits. All right, so the first thing I want you to do, let's just see if, I'm not going to read this out to you. Let's see if we remember what the notation is asking us for. Okay, so when you see C bar of x, you need to know that that means that I'm asking you for the average per unit, the average cost. So to find that, remember you do total cost divided by x. Okay, that's all there is to that. So B, I want you to find the derivative of that. Okay, the derivative of what you just found. Okay, and notice we can't do the derivative of something that looks like this. We're going to have to rewrite it so that we can use the power rule. So before I jump into finding the derivative, first I just need to talk about plain old C bar of x. Okay, and I'm going to need to rewrite this as, remember what I said, if it has a singular denominator, you're allowed to rewrite it as each term over the denominator. And notice the reason I might want to do that is because I'm going to be able to rewrite these. Like this would be 1,000 x to the negative 1 power. Notice here the x's would go away, and so I would just have 25. Here one of the x's would go away, and I would have minus 0.01x. Okay, so now that it looks like that, now I'm ready to find what I was supposed to find in part B, which was the derivative of this. So if you move the negative 1 to the front, you get negative 1,000 x to the negative 2. The derivative of a constant's always 0. Okay? The derivative of this, remember this is x to the first power, so if you bring the 1 to the front, the number stays the same, and if you bring the power down by 1, notice the x term goes away. Okay? So the derivative of the average cost is, again, a negative function, okay, and that shouldn't really shock us. Since the more items we make, generally speaking, the average cost per unit should go down. Not always, but generally. All right, so I want you to find C bar of x and C bar prime, sorry, not of x, of 10, and C bar prime of 10. And you're going to see this on test 1. I want you to briefly explain. When I say that, I just mean, like, if you get an answer of 4, I want you to tell me what that answer of 4 means. Is it $4? Is it $4 per unit? Is it a rate of change or something like that? I want you to indicate to me that you understand what it is that you're getting, not just write down a number and not really know where it came from. So if I want C bar of 10, I'm going to go up to part A, right, and I'm going to plug in 10. So I'm going to take that average cost formula from part A, and I'm going to plug in 10. So I'll let you do that on your calculator, but that would be $124. And make sure you write per something. So in this case, this is per drill bit. Okay, so this is the average cost per bit. Okay, so we're obviously not talking about little drill bits for your home tools, right? We're obviously talking about something a little more complicated than that, since it's kind of a high average cost. So if I ask you for C bar prime of 10, that means go to part B and plug in $10 there, right? So that would be negative 1,000 over 10 squared minus 0.01. So if I do that on my calculator, notice I get a negative number. Now a negative cost wouldn't make sense, but a negative rate of change for average cost makes complete sense, right? What this tells us is that the average cost per bit is not increasing, right? Because the slope is negative, it's actually decreasing by $10 and 1 cent per bit. All right, and then the last question on this problem, I want you to use the previous results to predict the average cost per bit if we bump up to 11 bits. So notice all of those previous numbers in part C were if we were at a production level of 10. And so I am asking you about one more, right? The next one. Okay, this wouldn't work if it wasn't the next item, but since it is, we already know that the average cost at 10 units is 124. And then we know that the rate of change here is that we're subtracting $10.01 at this level. So if you just take 124 minus $10.01, then it means if you were to up the production level to 11, now they're all at 113.99 per bit. Okay, it wouldn't work for the 12th item. It only really works for the next one, because frankly, at the 12th item, there might be a different rate of change. All right, so let's do maybe a quick profit question. Really, this is just seeing, do you know the new notation or not? So if I ask you to find the marginal profit, and profit is x squared minus 4x plus 1,000. When you see the word marginal, you need to think to yourself, I need to find derivative, okay? So the derivative of this would be 2x minus 4, okay? Notice I didn't ask for the marginal profit at a certain sales level or anything like that. If I would have, then let's say I would have asked for the marginal profit at 1,000 units, then you would have plugged in 1,000. Okay. Remember, it means the next item. So if I would have asked you for the 2,000 first unit, you actually plug in 2,000. Okay, so for our last question of the lesson, we are going to need to review something else from the algebra class before this one. So I want you to think about how you could find revenue if maybe it wasn't given to you. So before I tell you the formula, let's think about a scenario. Like, let's say that I had a small t-shirt company. Okay, revenue is the amount of money I bring in from my company, right? So how could I find revenue if I didn't know it? I would need to know, what am I selling my t-shirts for, right? Like, what am I bringing in per t-shirt? And then how many t-shirts am I selling? So revenue in general is always price times quantity. Okay. Notice little p in economics almost always means price. Capital P means profit, so you need to make sure you kind of distinguish between the two. And then X is just representative of the number of units. Okay, so sometimes you may not be given the revenue function right off the bat. You may have to find it. But that's usually not too difficult. So let's say that the price we're selling something for is P equals negative 0.02x plus 400. And let's say that I want you to find the marginal revenue and I want you to find the revenue from the sale of the 101st unit, excuse me. So the first thing is I asked you to find marginal revenue. Okay, so normally speaking, you would probably tell yourself, well, hey, I need to find the derivative. But I don't even have the revenue equation, right? So first, before I can begin, I'm going to have to find the revenue equation before I can take the derivative of that. So first, I'm going to use my equation that I just reviewed with you. I have to take price times quantity in order to find revenue. So notice our price equation is negative 0.02x plus 400. And I'm going to multiply x times that. This is kind of like distributive property, but it's just a little backwards. Okay. So my revenue equation then is going to be negative 0.02x squared plus 400x. I'm not going to circle that because that's not what the problem asked for, okay? But now I'm free to find what the problem really asked, which was now I need to find the derivative of what I just found, okay? So the derivative, if you move the 2 to the front, you will get negative 0.04x and then plus 400. Notice I moved the powers to the front. I subtracted 1 from the powers. Okay, so this is something I was asked to find, right? The derivative. And then the next thing is I need to pay attention to the fact that this means the next unit, right? So you have to ask yourself, like, if I want the 101st, how many items have already been assumed to have been produced up to this point? And the answer to that would be 100, right? So to find the 101st unit, I would actually do R prime of 100 because this means the revenue of the next item, which is exactly what I want, right? So if I want the next item, then I need to plug in 100. And so it would be negative 0.04 times 100, and then plus 400. So let's do that on our calculator. Negative 0.04 times 100 plus 400, and we get 396. Okay, so just to make sure we understand what the meaning of this 396 is, it's the fact that if we sell the 101st unit, it will bring in $396. Okay, it is not necessarily going to be true that selling a different numbered unit would bring in the same quantity of money. In other words, there's things in life that change price all the time, right? Like gas prices is a huge thing, right? So gas is not going to be the same Monday, probably even as it was on Friday, right? They're always changing gas prices. So just like that in, businesses that are not constant. Okay, lots of businesses change their price, and so they're actually bringing in different revenues at different times. Okay, so all Section 10.7 was really taking the derivatives that we've learned over the past couple of weeks and just applying those to economic principles. So when you hear the word marginal or see the word marginal, you need to think to yourself that you need to find the derivative since it represents a rate of change.